Welcome to The Explainer. Today, we're diving into an absolute masterclass on how to build a modern, AI-driven operating room scheduling platform for the year 2026. The operating room is the beating heart of any hospital. But let's be real. As anyone in healthcare tech knows, managing its schedule is notoriously chaotic. It's this constantly shifting puzzle of emergencies, delays, and a million moving parts.
Let's kick things off with a massive stake setter. 60 to 70%. That's the staggering proportion of all hospital patients who are admitted for some form of surgical intervention. Because of that incredibly high patient volume, the operating theater accounts for more than 40% of a hospital's total cost. If you're a hospital administrator or a system architect, you literally feel this pain every single day. Those numbers clearly dictate that intelligent scheduling isn't just a nice-to-have upgrade anymore, it's an absolute financial and operational necessity to keep the hospital afloat. But as we know, it is incredibly difficult to pull off.
So why is it so notoriously difficult? Well, mathematically speaking, scheduling an operating room is what computer scientists call an NP-hard problem. Basically, it's a class of mathematical problems so intrinsically complex that finding the absolute perfect solution among billions of permutations is computationally impossible in polynomial time. Think of it like playing a high-stakes game of Tetris on ultra-fast mode. But instead of geometric blocks, you're juggling human lives, massive budgets, exhausted surgeons, complex cleaning times, and strict deadlines all at once. If you lose, the hospitals bleed money, and patient care ultimately suffers. Which brings us to the million-dollar question. For all you developers and system architects out there, how on earth do we solve a puzzle with billions of permutations? How can we systematically build a blueprint to solve this massive puzzle and take those tiny, seemingly useless scheduling gaps and expand them into fully usable time slots? I'll tell you right now, traditional manual heuristics and whiteboard scheduling simply cannot handle this level of complexity anymore. We need a completely new architecture for 2026.
Part 1. Multimodal AI Duration Prediction. It's time to finally move beyond manual heuristics.
Look, in 2026, the old habit of just guessing how long a surgery will take or relying on simple historical averages is what leaves operating rooms sitting empty or causes those massive cascading delays. Legacy models used to rely entirely on structured data, things like a patient's age, their BMI, or their ASA score. And sure, that's useful information, but it completely misses the clinical nuance. Modern multimodal pipelines actually read the semantically rich preoperative procedure descriptions that clinicians document in their messy, complex clinical notes. By combining structured demographics with unstructured text, the AI actually captures the true complexity of a surgery. It knows whether a procedure is minimally invasive, a complex revision, or if it involves bilateral complications. The sheer performance leap we get from this multimodal approach is just incredible. When we compare traditional text encoding methods against contextual AI embeddings like Clinical BERT or Sentence BERT, the contextual AI drastically drops the mean absolute error down to roughly 26.4 minutes, with a proportional error of just 21.6%. Think about what getting nearly half an hour of precision back per surgery does for a daily schedule. Imagine what your clinical team could pull off with an extra 30 minutes found per room every single day. It proves conclusively that bringing in semantically rich clinical text reduces prediction error way better than relying on structured data alone. All right, Part 2, Real-Time Location Systems. We are adding physical context to the operating room. Because predicting time is really only half the battle, right? We need physical context to truly optimize the schedule. When evaluating RTLS, or real-time location systems, across things like accuracy, latency, interference, sensitivity, and cost, one clear winner emerges for the surgical environment, and that is ultra-wideband, or UWB technology. With its incredibly high accuracy and remarkably low latency, it completely dominates older tech like RFID and Wi-Fi. Those might be fine for tracking basic warehouse inventory, but they simply cannot offer the speed or the precision you need in a fast-paced operating room where every single second counts. So why does that sub-meter precision actually matter so much? Because ultra-wideband can pinpoint the exact location of your staff and your mobile equipment to within just 10 to 30 centimeters. This means no more nurses running down the halls desperately searching for infusion pumps or specialized surgical trays. In practice, this high-precision tracking can slash operating room turnover time by a massive 25 to 35%. If you are managing hospital operations, this is basically the holy grail of throughput. It allows hospitals to safely push more patients through their daily pipeline without burning out their clinical staff.
Moving right along to Part 3, Seamless EHR Workflow Integration. This is all about connecting the hospital's central nervous system.
Now, a highly predictive model is completely useless if your clinical staff can't interact with it natively. So let's look at how this integration builds out chronologically. Step 1. An event occurs in the EHR, like a surgery being scheduled or a sudden change in a patient's status. Step 2. An HL7v2 ADT message acts as an immediate trigger, alerting our system. Step 3. That trigger tells our FHIR APIs to execute a real-time data pull, ensuring the model has the absolute latest clinical picture. And finally, Step 4, the AI dynamically updates the schedule based on this fresh data. It is a seamless, real-time synchronization loop that just never stops.
To actually make this loop happen, we have to rely on some very specific integration gateways. For Cerner environments, we use the Open Interface for HL7v2 and the Millennium Gateway for FHIR and REST APIs. Over on the Epic side, we leverage outgoing ADT interfaces and precise encounter matching via the CSN. But honestly, the true magic lies in tools like Epic's CDS hooks. This allows us to surface AI predictions directly into the clinician's native view as a standard alert, no forcing an exhausted nurse to open some disruptive third-party application on a separate monitor. It just seamlessly works exactly where they already work.
And finally, Part 4, HIPAA compliance by design, the required 2026 security setup. As Tech Ahead COO Mukul Mayak rightly points out, we have to treat every single byte of protected health information, or PHI, surfaced to an AI model as a major compliance liability that absolutely must be justified. For the IT security professionals listening, this is exactly where you earn your keep. When your system creates vector embeddings to understand those clinical notes we talked about earlier, those embeddings are legally classified as PHI. If they're exposed, research shows they can easily be reverse engineered right back into patient data. And with a healthcare data breach today costing an average of $7.42 million, world-class security isn't just an afterthought, it is foundational. Which brings us to a hard, absolute, non-negotiable architectural rule. Utilizing consumer AI tools, like your standard ChatGPT or Claude, with patient data is a direct, inexcusable HIPAA violation. Why? Because they completely lack a business associate agreement, or BAA. To stay compliant, your architecture must exclusively use enterprise AI APIs, like Azure OpenAI or AWS Bedrock. These enterprise versions are deployed in strictly isolated compliant environments and are covered by an executed BAA, which guarantees that patient data is never ever used to train the vendor's public models.
Building on that, your 2026 development partner has to meet some incredibly strict requirements. You absolutely need those executed BAAs in place. For quality and security, you're looking at ISO 1345 for medical device rules if your AI provides clinical recommendations, and SOC 2 Type 2 for validated external controls. You also need ISO 42001 for AI governance, alongside immutable audit trails tracking every single prompt and response. And listen closely. Retrofitting these compliance measures after development is going to cost you 3 to 5 times more than building them natively. It absolutely must be designed into the architecture from day one.
So think about this. Your AI might be able to beautifully predict the future of your operating room, maximizing efficiency, improving patient flow, and saving millions of dollars. But is its underlying architecture truly designed to protect it? Take a really hard look at your own predictive software today. Is your data flow mapped out? Are your text embeddings actually encrypted? I really hope this architectural blueprint has given you the necessary tools to assess your own systems, ask the tough questions, and confidently build the future of healthcare. Thanks so much for joining me on this explainer, and keep learning.